Okay guys, going to take a little bit different approach on this video. What I want to do is I prepared a short PowerPoint. Let me get some coffee in me. A short PowerPoint on MANOVA, which is multivariate analysis of variance. And you can just think of this as doing multiple ANOVAs. And there's sometimes we need to do that, hence the reason for me teaching you this concept. First thing I want to do is generate this or motivate this in an example, and I think it's a great time to just kind of step back and kind of serve as a review what we've done so far. Remember, ANOVA is a technique which allows us to examine the difference in group means when we have more than two groups. Obviously, if we have two groups, we'll do a independent samples t-test. And I've got this example that I'm going to build upon all the way through this lecture, or through this PowerPoint. So what if we have three statistics professors here at Shawnee State, Dr. Dev Kota, who would join us in the fall, Heather Wall, who is currently with us as a full-time instructor, and me. And let's say we get together and we kind of don't necessarily agree on the best way to teach Math 1500. So Dr. Dev Kota says he'd like to teach it with a lecture with using my stat lab. Heather says use lecture with Stats Portal, and me, I think, use lecture and implement R. You know me in R, right? So to evaluate the instructional techniques, we'd carry out, a simple ANOVA and may look at the average scores on the Math 1500 final exam. Okay, so that's kind of old stuff. Thing to remember in the process is there are two estimates on the variance. We have the between variance and the within variance, and ultimately the ANOVA uses the F statistic to examine the relation, the ratio between the two. So guys, remember, if our test is statistically significant, it tells us that we need to do some post-hoc analysis to find out where the group means actually differ. And depending on whether the group variances are equal or not, we can choose a Tamhani or a Tukey HSD. And Tukey HSD is the one that we've used before. The final bullet there, you see that we can check these equal variance assumptions using the ratio of the largest variance to the smallest variance. Guys, sorry, I don't know what's up with this. And that should be 2 or smaller if we have homogeneity of variance. Okay, fast forward into a two-way ANOVA. As we should know now, a two-way ANOVA deals with two factors. And the focus of a two-way ANOVA really at the end of the day is to examine the interaction. If the interaction isn't statistically significant, then we drop back and look at the two main effects. But anyway, there will be three F ratios, one for main effect A, one for main effect B, and the third, which is the one that captures our attention, is the effect of the interaction. So, example, let's stay with the dependent variable being Math 1500 for final exam scores. Factor 1 being the teaching method, as we talked about before. And maybe there's some reason that we feel that there could be, some of the difference in these final exam scores may be contributed to whether it's an evening or day class. Evening class, although not across the board, but they typically have kind of non-traditional students. I really don't like that phrase, but it tells us what we need to know. And maybe we think there's a difference. Maybe we think that maybe lecture with R would work better for those in day classes, and maybe my stat lab would work better for those in the evening classes. So entering this factor 2 would allow us to look at the interaction between teaching method and the time at which the class was actually offered. So guys, fast forward into ANCOVA. This is where I provided, or at least introduced the idea of a covariate. The ANCOVA model has one dependent variable, which is quantitative, and two independent variables. One categorical being our factor or treatment, and the other being a quantitative covariate. Guys, you can have a categorical covariate, but we'll encounter that one if we'll cross that bridge if we ever need to. But for right now, let's just say that we've got we work with quantitative covariates. All right. So guys, at the bottom there, I tell you we want high correlation with the dependent variable. So we want our covariate to be highly correlated with our dependent variable, our quantitative dependent variable. But we want a low correlation if we have other covariates in the model. Okay? So assumptions for ANCOVA, as we've talked about before, we need the covariate to be independent across the groups. So we run a separate ANOVA with the covariate as our dependent variable across the treatment or factor. And we want homogeneity and regression slopes. And the way we do that is run ANCOVA with an interaction variable. If our interaction is statistically significant, then our assumption has been violated. Now we still have the same assumptions that we run with ANOVA, independence, normality, and equal variances. So an ANCOVA example may be still final exam scores for Math 1500. X1 is our categorical teaching technique, and our quantitative covariate may be ACT math subscore. Okay. Now this gets us to MANOVA. And MANOVA is a multivariate analysis of variance. And what we do here is we have more than one dependent variable. Now, a good way of thinking of that is let's think about this Math 1500 final exam score, which may be divided out into three sections: descriptive statistics, probability, and inference. Still, our independent factor here is the style of lecture, the type of lecture. And maybe we want to look at the differences across the three components of the final exam with the type of lecture. In this case, it would be a classic MANOVA design. Now, thinking ahead, you can see that maybe we could run a MANCOVA design here if we want to include the covariate ACT math subscore, which I think would be an excellent idea. So it's kind of all coming full circle here with the whole ANOVA. Well, really, well, I'll tell you what, let's look at the next screen. So why conduct a MANOVA instead of multiple ANOVAs? If you think about why we conduct ANOVA instead of multiple ANOVAs, why instead of conducting multiple t-tests, well, we inflate the type 1 error rate. So the similarities are there. We don't want to conduct ANOVAs because multiple ANOVAs because we inflate the error rate just like we would if we conducted multiple t-tests. Second bullet, none of the individual ANOVAs may produce a significant main effect on the dependent variable, but in combination they may. We'll see examples of that. And MANOVA accounts for the high correlations between the dependent variables. And that's something we want. We want to look at our correlation between our dependent variables, and we want them to be highly correlated when conducting a MANOVA. If they're not highly correlated, then I see no reason not to conduct multiple ANOVAs because they're just much easier to understand, and the process is just easier. So again, the motivation for conducting a MANOVA would be we have multiple dependent variables across a factor, and we go from there. Guys, assumptions for MANOVA. We want multivariate normality. We want the homogeneity of the covariance matrices, and we want independence. So this will all be illustrated in a future video. So let's get into an example. And so let me shut down PowerPoint. And I want to come up and show you an example of some data that I have. Now, what we've got here is we've got three groups. You might think of it as three treatments, three instructional techniques, you know, whatever. And we have two dependent variables, y1 and y2. So what I have done with this data is I put it into Excel. And you can see that when we put things into Excel, that on the lines we have to have cases, and on the verticals we have to have variables. I remember turned you guys loose our first on-campus session, and most of you got this wrong. Guess what? I did too, first time I did it. So anyway, we've got it coded correctly. And you can see that to save time, I've already gone ahead and you know, set my working directory and imported the data into R. All right, so I've attached it, and there's our data. So a very small, manageable data set there to deal with. Now, the first thing we'd want to do when we run ANOVA is we have to kind of bind the y1 and y2. And what we do with that is we use the function cbind. And we combine however many dependent variables that we have. Now, the MANOVA design is kind of wacky in a sense, because what actually happens is throughout the process it kind of takes the two models and it kind of smashes them together and creates what I would call a combined model, maybe a composite model. And it will compare each of the models to that composite. And if there's this drastic difference between the model and this composite, then we'll get statistical significance. So it's not really comparing the two models or three models against each other. It's creating this kind of linear composite and comparing the models to that. But anyway, let's go ahead and run a MANOVA, and I'm just going to call this fit1. And there's actually a command in R for MANOVA called MANOVA. So guys, we take our Y, which we've created from y1 and y2, and we run a fit1. Just as we've done before, we would run summary fit1, and we get this output. Now, there's three major test statistics that people use. Actually, I guess there would be four, but there's three that you see the most. P-Lies trace, which is the one I'm using here, and you can see that our result is statistically significant. Another very common test is Wilks. Now you can see that Wilks has a little different value. It's running a little different distribution. Notice the degrees of freedom are different, and notice our p-value is a little bit different. Another commonly reported test statistic for I don't know if I can spell this correctly or not. It's hoteling lolly. Let's see if that works. Wow, cool. Okay, again, another commonly reported test statistic for MANOVA is this hoteling lolly, and again, it's a different test statistic, but we also have different degrees of freedom in creating a little bit different p-value. Now, when things get really interesting, I've actually seen this before, is where you have maybe P-Lies trace that's statistically significant, and maybe Wilks is not, or vice versa. That creates kind of an interesting paradox in running a MANOVA. Okay. So anyway, we've got statistical significance. So the group means across Y1 and Y2 appear to differ across group. Now we can get a little bit better indication of what's going on here by doing what's called a let's see, how do we do that? Summary dot ANOVA for fit 1. That's not what it is. It's summary.AOV fit 1. Yeah, okay. Now what this does is it breaks our design into across the different responses. So this allows us to come in and, you know, if you look at this table, this is just a classic ANOVA table. And it allows us to examine the differences across Y1 and Y2. So we're kind of creating a no-no here by breaking these things apart. But you can see, and I'm pretty sure I'm right on this, let me just, if we had run just a separate ANOVA of, say, Y1 across group, okay, well, we actually get the same thing. Okay, so that's exactly what, I guess, what this is doing up here. I thought it was actually a little bit, something else was going on, but no, I was wrong. So that's really what the summary.AOV does in MANOVA, is it just breaks it down and conducts two ANOVAs. So it gives us an indication. There's a statistically significant difference in Y1, and there's a statistically significant difference in Y2 across the groups K1, K2, and K3. Now, what I would probably want to do here is I would want to do some multiple comparisons. And the multiple comparison could work like this. Let's say that we want to compare you know, across K1 and K2, and then maybe K2 and K3. And again, let me go back up and, you know, make sure that you're understanding what I mean by K1, K2, K3. These are just the subsets of the group. If we do that, we could do something like this. So now we're going to conduct multiple comparisons. And because we're doing multiple comparisons, we'd probably want to control for the type 1 error rate by maybe lowering our threshold. Instead of 0.05, we may want to look at 0.01. So I'm going to run a fit 2 and a MANOVA, and I want to run my Y across my well, let's do something a little different here, across my group, and then I want to set subset equal. Now here's where the fun starts. We're going to use a trick that I found. Alright, this should work. Now, what that's going to allow us to do is it's going to allow us to break our MANOVA down and just do a comparison between group 1 and group 2. So if I do summary fit 2, you can see that I'm just going to compare groups 1 and K1 and K2, and you can see that it has statistical significance at the 0.05 level. However, considering that we're going to construct multiple of these, I'm not impressed. I would want this to be statistically significant at the 0.01 level. So let's go ahead and see. So I want to run this one instead of a fit 2. I'm going to call this fit 3. And instead of K1 and K2, I'm going to run this as K1 and K3. Now, I have you know, statistical significance at the 0.01 level here, so you know, this has my attention. And I'm going to run, as you would expect, one more So I'm going to call this fit 4, and I want to compare K2 and K3. Alright. And I'm not expecting anything here, but we'll see what happens. Okay, so you know, again, at the 0.01 threshold, we would not have statistical significance. So again, let's control for the type 1 error rate, decrease our alpha value, and so guys, it appears that the difference in group means appears to be between the comparison of K1 and K3. All right, well, guys, I'm going to keep this one short. What I'll do is I just wanted this video to be honest with you, I don't have much time this morning. I've got to get in and teach an undergrad class and then teach another grad class this afternoon. But I wanted to get just an intro to MANOVA up first, just to get you thinking about MANOVA. The next video that you get will be a very thorough example. We'll set up hypothesis. We'll go in and you know, see how we report these values, do a little stronger interpretation, and we'll go from there, man. So guys, have a good one.